Good day! Before you watch this video, please make sure that you have already done the following prerequisites. Good luck! There are many complex parts to vector analysis. However, we're not going to dwell there. We're going to limit ourselves to the very basic. Vectors allows us to look at complex, multi-dimensional problems as a simpler group of one-dimensional problems. We will be concerning ourselves mostly with the definitions. The words may be a bit strange, but the ideas are very powerful. Math and science were invented by humans to describe and understand the world around us. We live in at least four-dimensional world governed through the passing of time and three space dimensions, up and down, left and right, and back and forth. We observe that there are some quantities and processes in our world that depends on directions in which they should occur. And there are some that do not. For example, at the heart of all mathematics are numbers. If I were to ask you, how many burgers did you have? You can say 3, and I would find that answer very perfectly satisfactory. The bare minimum number 3 is a magnitude, and sufficient enough to provide this information that I need. However, if I ask you, how far is your house? And you answered 3, then the information would be insufficient. And I would ask you, 3 what? Evidently, for this question, there are more information that I need. The bare minimum number 3 is no longer sufficient, and I require a denominate number, meaning I require a number with a name. Suppose you answered again, 3 kilometers. The number 3 is now named representing a certain number of kilometers. Such numbers are sometimes referred as scalars. If I were to next ask, how do I get to your house from here? And then you said, just walk 3 kilometers. Again, I would look at you quizzically. This time, not even a denominate, a number with a name, is enough. It is necessary to specify a distance or a magnitude, but in what direction? Mathematicians and scientists refer to these quantities as vector quantity. A quantity which does not depend on direction is called a scalar quantity, and a quantity that depends on direction is called vector quantity. In this episode of Agham Liknayan, Lesson 3, Discussion 1 to 4, you are going to learn how to add vectors using graphical and analytical method. Let's start. So a while ago, we have discussed the definition of a vector in a scalar physical quantity. We're now going to try to elaborate more on that. So as defined, scalars are physical quantities that has magnitude only. When you say magnitude only, these are quantities which has mathematical number and a unit. For example, 3 kilometers, 3 would be the magnitude, while kilometer would be the physical unit. Meanwhile, vectors are physical quantities that has both magnitude and direction. So when we say 3 kilometers, that would be 3 as the mathematical number, kilometer is the physical unit. However, it won't be enough. We should also add the direction. So 3 kilometers would now be 3 kilometers north or 3 kilometers east, and so on and so forth. Now, try to guess the following physical quantities and identify if they are a vector or a scalar quantity. Length is a scalar. Area is a scalar. And volume is also a scalar quantity. If you're going to observe, these are quantities of distances or length. Meaning, it doesn't require us to know what would be the direction of a certain object if we're talking about length. Why? It already makes sense on its own. For example, if we have this and try to measure it, using this ruler, so this would be 15.5 centimeter, and it would make sense already. So it will be considered as a scalar quantity. Again, please try to identify if they are scalar or a vector quantity. Speed is a scalar quantity. Displacement is a vector quantity. Energy is a scalar quantity. So, among this, ang naiba natin would be the displacement. Why? Because displacement is actually a vector quantity. Its counterpart is the distance, which is a scalar quantity. So why is displacement a vector quantity? By now, you should already know because I have given you a link that would actually tell you what's the difference. Temperature, lift, and mass. Try. Temperature is a scalar quantity. Lift is a vector quantity. Mass is also a scalar quantity. Now, why is now mass a scalar quantity? Because mass just defines the amount of substance in an object, so it doesn't require direction. Meanwhile, lift is a vector quantity because you cannot lift something without a direction. The only direction that if you lift an object would be upward, so it should be a vector quantity. There are a lot of other scalar and vector quantities, namely the following. For scalar, we have length, area, and volume, speed, mass and density, pressure, temperature, energy, entropy, work, and power. On the other side, we have vector. We have displacement, velocity, acceleration, momentum, force, lift, drag, thrust, and weight. So those are the list. Is there another additional scalar and vector quantities? Aside from being a physical quantity with both magnitude and direction, vectors are also considered as mathematical representations. This mathematical representation represent different physical quantities. Okay, this helps us navigate or interact with abstract concepts such as speed, velocity, acceleration. So, before we actually interact with those quantities, we need to represent them first. And vector has a main role for that. For example, we have the following. I'm going to switch on my full screen view. I'm going to click F11. F11. Ayun niya. There. For example, we have the following situations. So these situations can be analyzed or represented through vector notations or vector representation. Let's choose a pen. Here, a pen. For example, a man is pushing a box. So we can put here an arrow representing that there's a force being applied here. And for example, that would be 3 newtons. Other vector representations would be this. For example, if we have here a positive particle, and if it's a positive, it should emit these electric fields. And these electric fields that I have been drawing are vector representation also. If you have here a ball, and a ball is moving to the left, I put here an arrow, that is also a vector representation. If you have here a car, and the car is moving to the right, another vector representation. So you can see here, those abstract ideas are being represented through a physical medium, which are the arrows. Now, how do we write arrows? There are 2 concepts that would be combined with one principle. First, the length of the arrow signifies the magnitude of the vector. For example, here, we have here a longer arrow. We have here a short arrow. Meaning, in relation to each other, this should be 10 Newton. And this should be about, let's say, 5 Newton. Again, the length of the arrow signifies the magnitude of the vector. Next, the direction of the arrow signifies the direction of the vector. Meaning, if we have here a ball, We have here a ball that bounces for about, let's say, 30 degrees with this reference. If we try to represent that, we should also draw here an arrow there with a 30 degrees angle here in relation to this axis. Now, if we have here this value, for example, it's a cannonball being fired. If that is the angle there, for example, that is 30 degrees also on the x, on the positive x as its reference. If we try to represent that, we are going to draw here, this is the positive x, and this will now be our representation vector, which should be still 30 degrees because our physical object here is at an angle of 30 degrees in relation to the x-axis. Now, combining them, please remember that you can move vectors as long as you don't change its length and its direction. Again, you can move vectors as long as you don't change its length and its direction. Later on, you're going to see how we can use that when we try to solve on different problem-solving questions. We now know how to write vectors. However, we have said a while ago that vectors should have magnitude and direction. Now, how can we illustrate that? By using the concept of unit vectors. Unit vectors is a vector that only has the length of one unit. For example, if we have here the force of 6 Newton, unit vector would have to be multiplied on the magnitude itself. Meaning, we can write here x hat. Then, it can be interpreted as if it's 6n multiplied by 1. Since again, a unit vector is a vector, it should have a direction, but only have one unit. So what would be the purpose of this? The purpose now of unit vector is to define what is now the direction of this magnitude. So in this case, we have a positive x, meaning, if you write it down, 6n x hat, it means that the force is applied on the positive x-axis. So that will be towards east or towards the right. Sometimes, different materials or references uses different letters to indicate unit vectors. In our case, we're going to use the values x, y, and z hat. However, if you encounter a similar reference, I, j, k would also mean the same, indicating the different dimensions. For example, x hat and I hat indicate the horizontal dimension, y and j indicate the vertical dimension, while z and k hat indicates the 3 dimension. Another important topic is finding the component of a vector. In this illustration, we have here a resultant vector. So a resultant vector is the result of the interaction of its component. So in this case, it means this is caused by the interaction of component vector on the x-axis and its component vector in the y-axis. For example, if we have here a metal hoop which is tied on a rope and being pulled in this direction with a force of 4 newtons, and on the other side, it's also being pulled on this direction with a force of 3 newton. We can write here x hat, since it's being pulled on the x dimension. We can write here y hat, since it's being pulled on the y dimension. Now, we can only imagine that this metal hoop will neither go on the y direction and the x direction. It will go diagonally since it's being pulled by the interaction of the x and y dimension. In this illustration, it is safe to say that this vector, this resultant vector, has a component vector on the x-axis with a value of 4 newtons. Meanwhile, on the y-axis, this vector will have a value of 3 newtons. So those are the component vectors of this resultant vector. To summarize, it means that the resultant vector F, resultant, has component vectors fx hat plus fy hat. So this would be your resultant, and these two would now be your component vectors. Properly writing that, we're going to have f is equal to fx plus fy, plugging in the value which we have gathered a while ago. Fx would be 4 Newton x hat plus its y dimension, that would be 3 Newton y hat. So this is now how you write a vector in component form. Now you cannot add these two since they are on different dimension. However, we're going to discuss later how to actually find the value of our resultant vector using our component vectors. What if we want to find out the value of this f? To do that, we're going to use the Pythagorean theorem. First, we have to analyze this illustration as if it's a triangle. So if we have here our value, which is fx hat with a value of 4 Newton, and we have here again its y component with a value of 3 newtons. A while ago, I have told you to remember a certain principle, that we can actually move vectors as long as we don't change its angle and length, or change its magnitude and direction. So you can choose if you want to move fy or if you want to move fx for this image to be completed as a triangle. So in my case, I want fy to be moved, meaning I'm going to move it directly on this side. So this will now be my, so I'm going to use a ruler. Yan. So this is now my fy, which has a value of 3 newtons. Now I can now use the Pythagorean theorem since f is now the hypotenuse of this 2. So applying the Pythagorean theorem, we're going to have f is equal to square root of fx squared plus fy squared. Plugging in the value of fx and fy, we're going to have the square root of 4n x hat squared plus 3n y hat squared. So I'm not going to write anymore the units, so we can have a simpler equation here. So that will now be 16 plus 9. Adding that, we're going to have 25. Square root of 25, we're going to have 5 newtons. So the value of our force here, due to the interaction of fy and fx, is 5 newtons. That's now how you find the resultant vector, the value or the magnitude of the resultant vector, using the value of your component vectors. Okay, let's have some examples. So for this one, we want to find out the component vector of this resultant vector. How do we do that? First, you have to illustrate it. So I'm going to write here an illustration of that F is equal to 15 newtons, meaning this vector force, for example, we have here a cannonball being fired with a force of 15 newtons. Yan. And we want to find out what is now the component vectors of that force. So if this is our vector here, our resultant vector, we should have a component vector which is directed on the x-axis. We'll call that fx hat. And of course, a component vector on the y-axis, we'll call that fy hat. Again, as the principle, we can move vectors as long as we don't change its length and direction. So if this is directed upward, we'll just move it on the other side, but still it's directed upward. For illustration purposes, mapapansin natin na hindi ganong ayos yung line ko, but it serves its purpose. So we're going to have here fy hat. Now, analyzing this, you should have reviewed the SOHCAHTOA. So, if we have been given an angle here which is 28 degree, we have to first analyze if fx or fy is in the adjacent or the opposite side of that angle, which is 28 degrees, or which is this angle here. So let's analyze. If we try to search fx hat, makikita natin that it's actually on the adjacent side of the angle. So we're going to write here adjacent side. Meanwhile, fy is actually on the opposite side of this angle. So that would be opposite. Okay? So from SOHCAHTOA, we have adjacent. So we are going to use the CAH. So C-A-H. Meanwhile, this is the opposite. So we're going to use the SO. So that would be S-O-H. Now, plugging that, we have cosine theta is equal to the adjacent side over the hypotenuse. We'll have here sine theta is equal to the opposite side over the hypotenuse. Next step would be to put our values here in relation to our situation. So we're going to have cosine theta, whereas the theta or the angle is 28 degrees, is equal to the adjacent side. And in our situation, the adjacent side should be our fx. So that would be fx hat over the hypotenuse. The hypotenuse now is our resultant vector, which is f. So we're going to write here f. Let's now go to the fy. We'll have sine theta is equal to the opposite side, which is the fy itself, fy, and then the hypotenuse, which is, again, our resultant vector. Okay, so this is now, we now have to eliminate the f as its denominator. And to do that, we have to multiply both sides by f. Same thing here, multiply both sides by f. Then we'll cancel this, and then we're left with, and then switching the equation, we're going to have this formula in finding the fx. So fx would be equal to f cosine theta. And same thing here, fy would be equal to f sine theta. Okay? Now, plugging in the value, we're going to have f, which is 15 newtons. That would be 15. Cosine the angle, which is 28 degrees. So 28. Then here, we'll have still 15 sine 28 degrees. So please get your calculator and try to find out what are those values. So 15 cosine 28 is, we'll have 13.24. So 13.24 newtons. Don't forget to write the unit and what is the physical quantity it represent. Also, as a rule, if we have numbers na kasunod pa neto, we have to get just 2 decimal values. So, okay na yun. Then, for this one, we'll compute. Fy will now be equal to 15 sine 28. That will now be 7.04. 7.04 newtons. So, these are now our component of a vector for this situation. Problem. So we have here, this time, it's not directed on the x-axis. Rather, it's on the y-axis. However, we're still going to use the same principle. We're just going to point out that hindi laging cosine kapag x-axis, hindi din laging sine kapag y-axis. It would depend on the angle. Again, I would illustrate this by drawing it again here. So this is now our f, resultant vector f, which is a value of 20 newtons. Since we're just focusing on the magnitude, we'll put their absolute value. Then this f has a component vector in the x and y. So we're going to have here the x component fx hat and the y component fy hat. Now, it depends upon you if you want to move fy towards here or fx towards there. So in my case, I'll just move fx since in our last example, fy yung minove natin. So I'll move it here, fx, that will now be fx hat. And the angle for that would be 30 degrees. Doing our strategy a while ago, we'll have to analyze first if fx is the opposite or the adjacent. So in this case, fx hat is actually the opposite side of that angle. Hindi katulad kanina. And we have here fy hat, which is the adjacent already. So that is now the adjacent side. So this is O, opposite. So we'll now have to use the so on SOHCAHTOA on this situation and ka on this situation. So hindi na natin gagawin kanina yung pag-cancel out since you should actually learn how to do that in a gist para mas mabilis yung solving natin. Since finding out its vector component is the first step pa lang when we try problem solving on more complex topic. So, if this is opposite, we're going to have here fx is equal to the resultant vector. Since this is s, that would be sine theta. S sine theta. Meanwhile, on the other side, this would be fy should be equal to f, the resultant, cosine theta. Again, kung paano natin ito nakuha, please refer to the previous example. So plugging in the value, we have f, that would be 20 sine theta, which is our angle, 30 degrees. And this one, this would be 20 cosine 30 degrees. This will now become 20 sine 30 degree, 10. So this is 10 newtons. So we'll have here a force on the x-axis with a value of 10 newtons. Meanwhile, on the other side, we'll have 20 cosine 30 degrees. That is 17.32. So Fy is equal to 17.32 newtons. So those are now our component vector. Now, if we want to check, for example, if we want to check if this x and y actually are our component vectors, we can use the Pythagorean theorem to find out its resultant. And in this case, it should be 20. So let's do that. So our formula would be f should be equal to the square root of fx squared plus fy squared. That would be square root of 10 squared. Isa-isayin muna natin, 10 squared. We have here 100 newtons plus we'll have 17.32 squared. We'll have here 299.98, since that's 299.982. Square root of 100 plus 299.98. We have now the value of 19.99 newtons rounded off as 20 newtons, similar to our value here. So that's how you check. Again, remember that if you want to find the resultant of a vector, you have to use the Pythagorean theorem. Meanwhile, if you want to try to find out the component of a vector, you have to use the SOHCAHTOA following the angle of your illustration or your situation.